So we have an acute triangle with orthocenter H. Let's see what GEO King said. GEO King. Oh yeah, okay. That's what GEO King said. So O is the circumcenter. And AD is a diameter. So this is point D. And then we draw the circumcircle of AHD, where H is the orthocenter. So let me draw point H. I'm going to use the tools. I haven't seen too many problems with the circle AHD. It's kind of interesting. Let's, so yeah, I'm probably going to want to draw the feet of the altitudes. Okay, how do I make a good diagram here? Close this. AHD. I wanted to, is it possible to intersect both the segments AB and AC, or I don't think so. I think it's, yeah, I think I have to extend AC no matter what. So F, oh, I think there's a typo. I think it should be like E and F. Yeah, so I'll just say that's E and that's F. And then we want to draw, this is weird, the 9-point center of AEF. Okay, so here's triangle AEF. We want both the orthocenter and the 9-point center. Let me at least draw this, because we want to draw something with H, right? So yeah, we could say, I mean, that might be enough. Like we know H is a reflection of G over BC, right? And GD is parallel to BC. So maybe that's good enough to draw for that. But, okay, so J is the orthocenter. That's interesting. It's all the way over there. And then the 9-point center, I guess it's the midpoint of the orthocenter and the circumcenter, right? So we could kind of do it that way. Okay, so really oh, that's interesting. It happens to lie on EF. So I'll have to prove that. I'll call this L. So L is, so K is the 9-point center of AEF. Is that really true? Let me draw the 9-point circle. So the 9-point center lies on one of the sides. Wait, okay, so now it looks like P is a midpoint. This is weird. Yeah, interesting. So the 9-point center lies on one of the sides of the circle, of the 9-point circle. I don't know if I've seen that before. So yeah, so we have to prove a couple things here. Like there's a lot of things I just saw by using GeoGebra. So the midpoint of EF lies on AD. That's not sure that's obvious. So what do we want to prove? We want to show HJ. First of all, we want to show HJ is parallel to BC. And then we want to show KO is equal to KH. So I think JE is equal to, so JEL. There's just so much stuff here. So JE is equal to 2LN. We know that. One second, guys. I'll be right back. All right, thanks everyone for waiting. So yeah, if we reflect L over AF to U point L prime, then LL prime equals JE. Okay, so to prove AO bisects EF, suffices to show that AEHF is harmonic. Interesting. So is there something we can project through? Well, if we can show P, yeah, it's equivalent. I see what you're saying. Maybe we could project AEHF onto the circle ABC. So if we project through A onto it, we would get A. We'd have to draw the tangent to that circle at A. So basically, we need to show, if we draw the tangent to that circle at A, and it looks like that passes through J. So I don't know if that's obvious. Oh, no, it doesn't. But if I pick a point, so to show that AEHF is harmonic, it's the same as showing that wait, AO doesn't bisect EF. I'm confused. Oh yeah, I don't even think AO does bisect EF. I think that was that was a coincidence. Yeah. Coincidences in GeoGebra. Who needs them? Yeah. All right. So yeah, first I'm trying to show the first part. I wonder if J, B, and G are collinear. But it almost looks like JB's tangent, but I'm not sure if that's true either. No. But what if we reflect J over E? No, if we reflect J over AF, It should lie on that circle. Yeah. And it looks like this concurs, actually. So EMN is the 9-point circle. Is it obvious that EN is a diameter? So the circle EMN, it's gonna pass through the altitude. So yeah, these will concur. So how do we show? Yeah, we want to show HJ is parallel to BC. Yeah, I think we're going to want to draw this. So LL prime is equal to JE. So we want to calculate the distance from J to BC. I'm sure it's the same as distance from H to BC. You know what? Let me draw this. Just going to add a couple points here. All right. So how do you find the distance from J to BC? Yeah, we have to use. So we also want to show KO equals KH, but we know K is the midpoint of JL. And I wonder if OH is parallel to JL.
Michael.
Yes.
So could you draw the line HD?
Yes. So the whole line, right? Not just the segment.
No, just the segment. Yeah.
Okay.
Okay. So we can prove HD parallel to EF, right?
Okay.
That is because angle EAH is equal to angle CAD, which means that angle EAH angle equal to angle FAD. Yeah. So HD will be parallel to EF, and from the spiral similarity, we could show that triangle DEF is similar to triangle DBC.
Okay. Yeah. That makes sense.
And because and therefore triangle HFE will be similar to triangle DBC, which is similar to triangle HCB as well.
Yes.
Yeah. So if you call P is the midpoint of EF.
By the spiral similarity. We're defining P to be the midpoint of EF.
Yeah. So because triangle HEF is similar to triangle HBC, right? So angle P is the midpoint of EF and U is the midpoint of BC. So angle HBE will be equal to angle HUB, right?
HPE will equal HUB. Yeah.
Yeah. And because HU is parallel to EP, so HB will be parallel to BC.
Okay, so then HP will be parallel to BC.
Yeah, and we need JH to be parallel to BC, right?
Yeah.
Therefore, we need JHB is collinear.
Okay. All right.
And so you define L as the center of the circumcircle of AEF, right? Yeah. Could you draw the diameter A prime?
Yeah. Hold on just a sec.
Yeah.
Sorry.
Okay. So if we could prove that A prime, A prime is parallel to EF. So A prime is parallel to EF, which is parallel to HD, and because APD is collinear, so HBA prime will be collinear as well.
A, P, and D are collinear means that H, P, and A prime would be collinear.
Right?
Yes.
Oh, did we prove that AD cross over the midpoint of EF?
Yeah, I was wondering that. Like, did we ever prove that P is the midpoint of EF? I'm not sure. So, like, I think you could show that P lies on this circle through like an angle chase you did. It's probably not. Yeah, if I write it out step by step, maybe it'll make it easier. So let me delete some of these things. AJ, so yeah, I think Geo King noticed something interesting. And so okay, let me write out what we know step by step. So, but basically we know that yeah, we just don't know that P is like the midpoint of the F, right? But like, so dat, if we did know that P is the midpoint of EF, do you think that could solve the problem?
I think yes.
Oh, wait. Khan said that AD doesn't bisect EF. It looks from here, it looks like it does. But P, yeah, but we want to, yeah. So if we could show P is the midpoint of EF, then
How do we define P?
yeah, let me just start writing stuff out. So yeah,
Yeah, just define D as the midpoint of EF.
okay. So so P is defined to be the midpoint of EF.
Yeah.
And so yeah, we know U is the midpoint of BC. So it's
from the spiral similarity, we have that triangle DEF is similar to triangle DBC. Yeah.
okay. So
Yeah.
so can we show that P has to lie on A prime H, or is that
Yeah, we could prove that.
okay. So okay, so yeah, I'll do it like that. So let me type this out. So triangle DBC is similar to DEF. I'll just start out saying that by a spiral similarity at D. Triangle DBC is similar to triangle DEF. Which is similar to triangle HEF, which is similar to triangle HBC. Yeah, we have all those different similarities. And then angle EAH equals angle FAD means that EF is parallel to DH.
I think you should try this first. This before yeah.
Okay.
Because if we have EF parallel to HD, we yeah. Yes.
Okay.
Okay.
So let P be the midpoint of EF. I'll say let P and U be the midpoints of EF and DH. That.
Yeah. So yeah. So that triangle HUB will be equal to triangle HPE.
Similar to HPE, yeah. So this. All right.
Yeah. So angle HUB will be equal to angle HPE.
And so, but HUB is also, so basically that shows that HP is parallel to BC, right?
Yeah.
Because, so angle HUB equals angle HPE, which I'll just say, I'll write it like this. I'll just say this implies HP is parallel to BC. BC. And that's because HD is parallel to EF.
Yeah.
Yeah.
Yeah. So if you call A prime is the diameter, so HA prime will be perpendicular to HA, which is parallel to BC.
Okay, so let AA prime be a diameter AC. Then since PH is perpendicular to AH, that means that A prime, P, and H are collinear.
Yeah, and because J is the orthocenter of triangle AEF, so A prime, P, and J is collinear.
Okay, so because H is the
J is the orthocenter of AEF. So A prime, P, and J is collinear.
Oh, okay. So because P is the midpoint of EF.
Yeah,
okay.
Yes.
So J is the orthocenter of. That means that A prime, P, and J are collinear. Yeah, I didn't realize that. Okay, so that's a pretty big step right there. Oh, I spelled this wrong. And then once we know that, let's see. So really, yeah, I'm just going to leave those there for now. But okay, so, and then once we know that, it's pretty obvious that then HJ is parallel to BC. So yeah, we use that fact so I'll say it's well known that HU and B are collinear because I did use that fact. Oh no, I actually define U to be the midpoint of HD, so I don't even need, but then I use the fact that U is the midpoint of BC. So I'll say it's well known that U is the midpoint of BC.
Why is HP perpendicular to AH?
Why is what?
HP perpendicular to AH.
Because HB is parallel to BC.
HP parallel to BC. Oh, okay.
Okay, so here I'll say it's well known that U is the midpoint of BC. So yeah, HJ is parallel to BC. Now let's see if we could solve the second part of the problem. So we want to show KO is equal to KH. Oh, so actually, you know what? K does not lie on EF. I don't know why I thought it did. Interesting. Yeah, so there were a couple things in the original diagram that like look true but aren't actually true. So once we know that, maybe the first part helps us prove the second part. Because it looked like, let's see, is OH parallel to something?
Could you draw the 9-point center of the triangle ABC?
Yeah. So that will be the midpoint of OH.
Yeah.
So we call it V. Let's try to, there we go. So yeah, KJ is equal to KL. It almost looks like, so yeah, L is the midpoint of A prime. So let's see. So maybe we could show K has the same power with respect to two different circles. I don't know. Okay, so yeah, well, another way to do it is we want to show that KB is perpendicular to OH. So yeah, how do we use that?
Could you draw into the 2-9 circle? Yeah.
Okay, so so that's one of the 9-point circles. Do you want me to draw the other 9-point circle too?
Yeah, please.
Okay, so that would be IU. I think N.
No. Yeah. Oh no. It is not N.
It's not N.
And the first one you draw wrong as well.
It would be this W right here.
No. The first one, the 9-point circle of AEF, it does not pass through L.
Oh, it passes through L.
No, it does not pass through L. It must pass through N.
Oh, I didn't draw the first one, right? Okay.
Yeah. It should be M, N, and P. No, M, M, N, P.
Sorry.
M, 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 N, and P.
All right. M, N, and P.
Yes.
There we go.
Yeah.
Do you want me to draw the one for ABC also, or no?
Yeah, it should be S, I, and U. Yeah.
So the centers are V and K. So V is the midpoint of OH and K is the midpoint of LJ. And we want to show, like, if we could show KV is perpendicular to OH, that would solve it. So
What if we can determine the two radical axes of the circle and prove it parallel to OH? I'm not really sure, I'm just predicting.
wait, so you want to draw the radical axis of
Maybe you just check if it passes to any special points, and if not, then just delete it.
okay. Yeah, I'll check out the radical axis. So this point and this point. Is this, check this. I wonder if AA1 is parallel to BC. No. Yeah, I'm not sure if the radical axis passes through something
Yeah,
interesting.
maybe it doesn't work. You can delete it.
I think so. KO.
Could you delete the line? No, just hide the line. Yeah, that line.
Yes.
Yes, and could you draw the midpoint of GA, JA, midpoint of JA and
Okay.
HA? Yeah,
JA and HA.
yeah, and delete the point R as well. Yeah,
All right.
yeah. So W, Z, and L is collinear.
Okay.
Yeah. And WK and P is collinear.
Sorry. WK and P.
Yeah.
So I wonder. Is K the circumcenter of ZEHO?
Yeah, I doubt that too.
Okay, so that's what you're.
Yeah.
Oh, but E doesn't lie on it, so Z. It would just be
Z, O, and H. Yeah.
Z, O, and H.
Yeah. Yeah, I could prove. If we could prove that, let's say K lie on the perpendicular, not the perpendicular bisector of ZH.
Mm-hmm.
Yeah. So and we need K lie on the perpendicular of ZO as well.
So I think K is on the perpendicular bisector of ZH because so we know that AL is LA prime. So then we know that WK is KP, right? And if WK is KP, then basically that means K is the same distance from those two lines, right? So KZ is equal to KH, right? So yeah, I think it's easy to show that KZ is equal to KH. So did you say once you know that, then you can prove that they're equal to KO?
Yeah, because if K lie on the perpendicular bisector of ZO, so K will be the center of the perpendicular, so KH will be equal to KO.
Okay, so it's ZO, yeah, that we want to show.
Wait, so we need HE0 cyclic too, right?
I don't think HE lies on that circle. So if we draw, I think it's just ZO and H because, so it looks like it there, but if I move the diagram, you can see E's not on that circle. Yeah, like in that picture. So yeah, E isn't a part of it. So O is the midpoint of AD. So we want to show KZ is equal to KO. So let's see, K, it's the center of this circle right here. Wait. Can we find congruent triangles somehow? Let's see.
Can you reflect L over EF?
L over EF.
Yeah.
There we go.
if we can prove that L prime H equal L prime D, then I think a homotopy is solved.
If we can show that L prime and what?
L prime H equals L prime D.
Okay.
But isn't that just obvious?
Yeah, I think it's obvious because, well,
Then a homotopy taking it takes L prime to K, takes D to O, takes H to Z.
so if it takes L prime to K, it takes, wait, a homotopy that takes L prime to K, or what did you say?
Yeah, center at A, center at A.
Oh, centered at A.
Yeah, with ratio 1/2. Do you remember the previous problem where we reflect the center of the circle over a line, and then it is collinear with A in the Euler circle, the center of the 9-point circle?
Yeah. So basically KZ would be half of HL prime, right?
Yeah. And K always half of L prime D, and L prime H is equal to L prime D. So yeah, it's
okay.
just like that.
So I think this might do it. Okay, so let L prime be the reflection of L over EF. And then, let's see. So, is it obvious that L prime D is equal to L prime H?
Yeah, it is obvious.
Because H is parallel to EF. Yeah.
Because HT is parallel to EF. So yeah, so so we have H. Hold on 1 second. Because L prime is the center of the circle, so LP is basically perpendicular to EF. So yeah, that's true. And then then we have A.
Yeah, and then we have WA is equal to PL, which is equal to PL prime.
Yeah.
Yeah.
So WA is PL, which is PL prime.
So K will be the midpoint of AL prime.
Okay, so WA is equal to PL, which is equal to PL prime. And so KH.
So the homotopy center A will take H to Z, L prime to K, and D to O. Therefore, KZ will be equal to KO.
Okay, so the homotopy about A takes L prime HD to KZO. All right. So that takes it to triangle KZO. And so that means that, or KHO. So that means that KO is equal to KH. Hey, Stefan, thanks for hopping in. All right, let me just make some more room and then I will hop on to the other problem that we didn't solve. So a lot going on in this diagram.
Could we return to the first problem? I think I have a solution for it.
Oh, you have a solution to it?
Yeah.
Ah, nice. All right. All right.
All right. So if we could prove that J is the midpoint of arc dB, so the problem will be solved, right?
Yeah.
Yeah. So where's P? Yeah. So let's say could you draw line KR and KQ?
KR and KQ. Okay.
Yeah. The whole line, not the segment.
Okay.
Yeah. Yeah.
All right.
All right. So let's say KR cut the circumcircle of ADR at one point. Yeah. Yeah, that point will be K will be midpoint of LR.
Okay. Yeah, that's true
Yeah.
by symmetry.
Yeah. So therefore, KL times KR will be equal to KA times KP, right?
Mm-hmm.
Which is KR times KR square will be equal to KP times KC, right?
KR squared is KP times KC.
Yeah.
Wait,
Because
how do you?
KA is equal to KC. Because KR times KL is equal to KA times KP.
Times KP. Oh, so it's KP times KC. Yeah, okay. That makes sense.
Yeah, therefore KR square is equal to KP times KC. And from symmetry, KQR will be equal to KQ square. It will be equal to KP times KC as well.
Okay. So
Okay,
QQ is
so
equal to KR.
yeah, so the thing is that we need arc JD will be equal to arc JB, right?
Yes.
Yeah, and but K is the midpoint of DB, which we need JK will be perpendicular to DB, right?
Yes.
Yeah, and if we use the inversion center K with the ratio KQ square, C will become P, right? And
Yes.
the circle through ABCD will become the circle with the center K and pass to P.
Yeah. So yes. So we could draw. So.
No, yeah, the first two, yeah.
Sorry.
Yeah. No, the first one, not that one.
Oh yeah, you're right.
Yeah. Yeah. Yeah, the big circle will become that circle, right?
Yeah.
So and the circle RQC will become circle RQP because C come to B.
Yes.
Yeah. Yeah, could you let two circle cut at another point except P?
This point?
No. Yeah. Circle. No. Circle. No. Not that circle. The circle with center K. Yeah.
Oh, okay.
No, center K cut the circle QPR, not QP.
Oh, it's hard to see. Okay,
Yeah.
so
That point. Yeah. You could move. No.
yeah.
Let's move C.
Move C. Okay.
Yeah.
There we go.
No.
Or do you want me to move?
Minimize.
Oops, sorry. But now Q doesn't look so good. Let me see if I can.
Let's say be near B.
I think this looks okay, right?
Okay. That's okay.
Or did you want me to do it more like this?
No. Just let it. Yeah.
Whoops, sorry. I think I messed it up a little bit. Let me fix it.
Yeah. That is okay. Yeah.
Yeah.
So because J is the circle ABCD, cut circle QRC. So S. So J will become to S because S is the circle with center K. Cut the circle QPR, right?
Yes.
Yeah. And so therefore we need KJ perpendicular to DB, which is KS perpendicular to DB, right?
Right.
Yeah. And we could easily solve that because let's say triangle QKR one a point P and KD and KB is the so
I think it's kind of obvious because basically
yeah.
what you're saying, like KR is equal to KQ, right?
Yeah.
So the circle.
Could you? Yeah. So triangle KPR will be equal to triangle KSQ.
KPR and KSQ are congruent.
Yeah. Right.
Yeah. Yes.
Yeah. So therefore, angle SKQ will be equal to angle PKR.
Yeah. So ultimately, we want to show that.
That angle SKB is 90 degree.
Okay.
Yeah. Kind of obvious to say. Yeah. Two triangle are congruent, so you have an angle PKR is equal to angle SKQ, right?
Yeah.
And PKR plus PKQ is 90 degree, right?
Yeah. So that's awesome.
And PKQ is equal to BKQ.
Yeah.
Yeah.
Okay.
So yeah.
I think I'm going to start writing it up. That's a very, very nice idea. Yeah, showing that KQ equals KR, that really helps solve it. So let me hide this. Okay, so we want to let K be the center of the rectangle, ABCD. And then we have, so let the perpendicular bisector of B, or I'll just say let KQ, let KR meet the circle PAD again at L. And then similarly, let KQ meet PAB again at O. Okay, so first we have KL is equal to KR. So KQ equals KO by symmetry. So we have KQ squared equals KQ times KO. Which is equal to KP times KA, is equal to KP times KC. And then similarly, we have KR squared is equal to KP times KC. And that means that KQ equals KR. And then once we know that, okay, so we want to show that J, we haven't defined J yet. So let J be the intersection of CQR and the circle ABCD. And we want to consider an inversion centered at K with radius KR.
Actually, we don't need the inversion, Michael.
Okay.
I think we don't need the inversion.
Okay.
That is maybe yeah. So triangle KRC will be equal to triangle KQJ.
KQJ,
right?
KQJ and KRC, we want to show are congruent.
Yeah.
Okay.
We have KR equal to KQ and KJ is equal to KC.
How do we know KJ is equal to KC?
Because K is the center.
Center.
Yeah.
So, so KR equals KQ and KC equals KJ. Then for the angles.
No. Let's say if you call the center of the circle CRQ.
Okay.
Yeah.
I'm going to delete these two circles. Just
yeah, just delete them. I might overcomplicated this. Yeah.
It's all right.
So TR will be equal to TQ, right?
Mm-hmm.
So TK will be perpendicular to RQ.
Mm-hmm.
Yeah, and TC will be equal to TJ, right?
Yes.
So KT will be perpendicular to CJ as well.
Wait. So I get like KT is perpendicular to QR.
Yeah, and it is perpendicular to CJ as well.
Oh, because basically KTC
because K is the center of the circle and T is the center of circle as well, and two circles intersect at C and J.
Okay, so by symmetry, so KTC is congruent to KTJ.
Yeah, so yeah, KT will be perpendicular to CJ. Therefore, RQ will be parallel to CJ, and so that CR will be equal to JQ.
Okay.
Yeah.
So we have KT is perpendicular to CJ. That's since K and T are both centers of circles. So that means KT is, so these two kind of imply that RQ is parallel to CJ. Yeah. So I'll say that means KT is perpendicular. Since KT is perpendicular to CJ, okay, so now we need to show that J is, we want to show that JK is perpendicular to BD, yeah. And that should be an angle chase because we have angle JKB is JKM plus MKB. So and that's equal to angle CKR plus plus angle
CKQ, yeah.
CKR plus BKQ.
BKQ is CKQ.
Wait, hold on a sec. Give me just a second. So this is JK. Oh, JKQ plus QKB. Yeah, so this, yeah, that's what you're saying. So, and then JKQ is CKR plus CKQ.
And that will be RKQ. Yeah.
Right. Which is angle RKQ. So since JK is perpendicular to BB, J is the midpoint of the arc. So J is the midpoint of arc BCD. And yeah, this is the hardest of them that we've done so far, although there's still one more that we didn't solve. And so If that's true, then yeah, it's a spiral similarity. But basically, I'm just going to use congruent triangles because basically we have JD is equal to JB, and basically we want to show triangle JND is congruent to JMB, but we have it's true by angle side angle. So so we have, I'll say it like this. So we have JD equals JB, and then we have angle JDN equals angle JBM, and then we have angle JNC. I'll say JNC is JMC.
No, Michael, just from the spiral similarity, triangle JMB is similar to triangle JND.
They're actually congruent, right? Well, yeah, okay. So we could just say that. I mean, well, I was just going to use angle side angle, but yeah. So that I'll just write that too. So triangle JBN similar to triangle JBM.
Yeah, and JB is equal to JD.
Yes. So we have JB equals JD, means that BM equals DM. All right, that was a nice one. So we have a couple more minutes. So I'll just show you guys the last problem. We'll see if, I'm not sure if we'll be able to solve it, but it's worth just looking at. Sometimes if I do it really low, it might not show up on YouTube. So I will try to move this just a tiny bit. There we go. That was a cool one. So the problem that we didn't get to yet, this one. So it's like you have a cyclic quadrilateral, A, B, C, D. And you draw like all the different so you basically make like a complete quadrilateral, right? So let me draw the diagonals. So O is the center of the circle. And I is the intersection of the diagonals. And BA, and this should be like DA and BC, I think. DA and BC. Let me make sure E and F aren't switched. So that's, because yeah, the original problem I think had like a typo. And then we draw the Gauss line of ABCD. So there was another problem. So yeah, I didn't use exactly the Gauss line, but we did something similar to the Gauss line on our. So yeah, I think H and I are too close. So yeah, that looks a little better. So GHJ is the Gauss line, and we want to see where it meets all the sides. So MNPQ. So I'm going to rename these in just a second. So AB, it meets at M. And then BC, it meets at N. CD meets at P. And DA, it meets at Q. We want to show the circle with diameter OI is tan. So we could just pick one of those circles, like let's say ENQ. Is that a good circle? What about FMP? I think might be better. Yeah, let's do FMP. So the circle with diameter OI, we want to show it's like tangent to that circle. So let me draw it. Interesting. Oh, does it pass through G and H? Or is that a cool?
Yeah, definitely, because OG is perpendicular to GI.
Because OG is perpendicular to GI. Ah, that makes sense. So yeah, so this is cyclic and K is the center of it. Okay. Let me hide, make it look nicer. Then this, and then this, and I think that should be everything. Yeah, it's kind of interesting. So yeah, really it's like this circumcircle of OGHI. Yeah, I don't even know if we really need K. I'm just gonna hide K.
Could you extend the line? Could you draw the line FI?
FI, yeah. Oh, you want to see what passes through the or the tangency point? Yeah, it looks like it.
It might, yeah.
Yeah, I think it does.
Yeah, they does.
Yeah. So we could let FI meet the circle at a point, and then we could try to show it. I guess that's one thing we could do.
OE passes through the tangency point, looks like.
Okay, that's interesting. I don't, yeah, so yeah, it looks like, yeah, these are like perpendicular, those two lines. So yeah, we know, well, we know IF and EO are perpendicular by Burckhardt theorem.
Yeah, I is the orthocenter of triangle EF and O.
Yeah. So yeah, if one is true, then the other has to be true. So yeah, show their tangent. We could either let IF intersect the circle at a point, or we could let EO intersect it at a point. And then we want to show that it's actually tangent at that point. Let me draw the center of this circle. Oh, does it really lie on AB? No, it just looked like it.
Can you label the intersection of can you label the point of tangency of the two circles?
Yeah.
So I think we can approach this way by proving that RG and RH are orthogonal in angle MRP.
Ah, so you want to show angle MPG is angle PRH.
Not really. I think we should prove by using like ratio to prove that they are orthogonal.
Okay.
Like maybe finding a way to prove that GM over GP times HM over HP equals RM squared over RP squared.
Okay.
So, and I think that RM squared over RP squared is RA squared over RC squared, because I think it's because of a spiral similarity.
Okay, because RMC or RPM is similar to RAC, is that true?
Yeah, yeah, is that true? I can prove it.
Okay.
Maybe we'll find a way to do this quick before the session ends.
Okay. But so basically RPM is similar to RAC, right?
Yeah, it is, because yeah, I can use spiral similarities and stuff.
Okay. But if that's true, that would give us some more cyclic quadrilaterals, because that would mean RPCG is cyclic. Yeah, and then also RGAM is cyclic. Okay, so I'm just going to hide those for now, just so it doesn't look as crowded. But you were saying, so what lines do we want to show are isogonal?
RG and RH.
And you want to show they're isogonal with respect to RPM, PRM?
Yeah, MRP.
Okay. So, but angle GRM would equal angle GAF, which would be G. So I think if somehow, like if you know those are similar, like can you prove that AMGR is cyclic and CPRG is cyclic? Because if you could do that, then that would basically solve it. Because then we would have, I'll write it out quickly. So suppose GRAM and GRPC are cyclic. I guess we don't even really know point R exists yet, but let's say it did.
Well, we can define R as the altitude from A onto O, from F onto OE, and by the proof of the Brocard's theorem, R lies on RIDA and RICD is also cyclic, and as well as AORD and BORC.
Okay, so we could define R to be the intersection of AI and EO. All right. FI. Okay. And then, what were the quadrilaterals that you said we could show are cyclic?
I don't know if we should draw it out because it will be a little, too.
Okay.
But, we can prove that BIRA and CIRD is cyclic, and
Okay.
AORD and.
So we could prove that. I'm not going to write out the whole thing, but we could prove that basically.
Sorry, Michael, did you say that if we can prove AMGR is cyclic, then we are done?
I'm not sure, but I think possibly. So let's see. Yeah, we started a couple minutes later, so okay, so that's cyclic. Okay, so if we're defining it that way, we know it lies on the smaller circle, but we don't know yet that it lies on this circle. So we want to show AMPR is cyclic. But yeah, if we know that these two are cyclic, then it would follow that APMR is cyclic. Because then we would have angle, basically, because then we'd have angle RMP is RMG, which would be RAG. Well, actually, I'm not sure now.
Yeah, and we can prove that no, actually we can use power over point. I think IA times IC is wait, no, I'm wrong.
I have shown this problem maybe some months ago, and the key part of this problem is using the spiral similarity.
Okay.
You can group the ratio equal ratio MA over MB is equal PC over PD just by using Menelaus theorem.
Menelaus.
Yes, Menelaus theorem, and so
and
that
I
you
use
can
that
have,
to prove.
yeah, you can have a similar triangle RMA is similar to triangle RPC.
Okay.
Yeah, that's what I said later before. We proved those two similar triangles by using the property that he said.
Okay. All right. I don't think I'm gonna have time to write it all out here. But yeah, let's just talk about it for a couple more minutes. So basically you're saying AM over MB is CP over PD. And you prove that with Menelaus's theorem?
We can use the law of sines too. Yeah, that is pretty easy.
Okay. And then once you know that, you can kind of show RMA is similar to RPC. That's what you're saying?
Yeah.
Okay, so I'm gonna write an outline. So I'll say AM over MB is equal to CP over PD. Using law of sines. And then we have RMA is similar to RPC. So yeah, I'm just gonna like abbreviate a bunch of stuff here. So I know we're a little bit over. And then from there, you can kind of prove that the two circles are tangent. So do you know how to do like the last step to show that? Well, once we show that APRM is cyclic, so this shows that FMRP is cyclic, right? And yeah, I think it's not too much longer before you can prove this. I'm going to stop here But yeah, this is really interesting ideas. So thanks everyone again for participating. I know this it's 3 hours, so it's I thank all of you for your commitment and for helping support the channel. And for everyone watching, if you would like to join future sessions, feel free to email me at mgreenb801@gmail.com. It's going to be in the description of the video, and we meet on Sundays at 8 a.m. US Central Time. Thank you and have a good one.